Right now we're watching 20,000 games played by an AI as it explores the world of Pokemon Red. In the beginning, it starts with no knowledge whatsoever and is only capable of pressing random buttons. But throughout 5 years of simulated game time, it gains many capabilities by learning from its experiences. Eventually the AI is able to catch Pokemon, evolve them, and defeat a gym leader. At one point it even manages to exploit the game's random number generator. But perhaps more fascinating than its successes are the ways that it fails, which are surprisingly relatable to our own human experiences. It turns out that studying the behavior of an algorithm can actually teach us a lot about ourselves. In this video, analyze the strategies it learns. At the end, I'll go deeper into some technical details and show you how to download and run the program yourself. This part will inevitably contain much more technical terminology. First off, the specific reinforcement learning algorithm used to train this AI is called proximal policy optimization. It's a pretty standard modern reinforcement learning algorithm, and even though it was originally designed in the context of games and robotics, it's also been used as the final step in creating useful large language models. However, while reinforcement learning does sometimes feel like magic, it can actually be an incredibly difficult tool to apply in practice. The fundamental challenge of machine learning is getting a program to do something without explicitly telling it how to do it. This means that if your model isn't behaving the way you intended, you have to figure out how to improve it indirectly in terms of its learning algorithm or training data. Online reinforcement learning adds an additional layer of indirection on top of this. The training data being fed into your model is no longer stationary and in your control, but is itself a product of the model's behavior at an earlier point in time. This feedback loop leads to emergent behavior that can be impossible to predict. So here are some strategies to engage these challenges without institutional scale resources. First, it may be necessary to simplify your problem to work around the limitations of the tools. You might have noticed earlier in the video that the AI wasn't actually starting from the very beginning of the game. Here you can see an early version of the AI, which does start from the very beginning. It doesn't have any issue choosing a Pokemon and winning its first battle. The problem comes a bit later when it's necessary to backtrack from Viridian City to Pallet Town. This is because the exploration reward doesn't give it any incentive to return to an area it's already visited. It might be possible to solve this by hacking in special rewards for just this scenario, but I decided that simply skipping past this was a better use of time. The modified start point is still very close to the original, and by giving the AI Squirtle by default, it has a better chance of success later on. Next, it's important to find a setup that allows you to iterate on experiments within a reasonable amount of time and cost. In many cases, the bottleneck will be simulating or operating the environment that the AI is interacting with. In our case, the environment is Pokemon Red running on the Game Boy emulator Pi-Boy. This emulator runs in the ballpark of 20 times normal speed on a single modern CPU core. Running many games in parallel on a large server with many cores allows us to effectively gather interactions with the environment at over 1,000 times faster than normal speed. This means each learning iteration with a batch of 40 games, each lasting 2 hours, will complete in around 6 minutes. If we use a small model as the policy, its inference and training time will be negligible, especially if we use a GPU. This means we can get results from small experiments in minutes to hours, and a full training run will take a few days. This can easily get quite expensive. Using the cheapest possible cloud options, a single full training run costs around $50. All of the experiments run in this project combined cost a total of around $1,000. However, if you're not careful how you choose and manage these resources, it's easy to spend many times more. Next, you'll want to carefully consider how the AI interacts with the environment and how your reward function is designed. The choices I made in this project certainly are not all optimal, but I'll describe at least some of the considerations that went into them. For example, the AI observes the screen and chooses an action once every 24 frames. This is just enough time for the player to move one grid space in the world, so whenever the AI observes the screen, it will always be aligned perfectly on one of the grid cells. This makes the exploration reward much more effective because it significantly limits the number of possible screens that can be seen. The component that makes decisions, called the policy, is represented by a small convolutional neural network. Notably, it's non-recurrent, which means that it actually has no internal memory of the past. This was done to improve training stability, convergence speed, and simplicity. So how does it make decisions with no memory of the past? Well, first, the 3 most recent screens are stacked together to create a simple form of short-term memory. Second, some basic information about the game's state is encoded as visual status bars. These display hit points, total levels, and exploration progress. A more conventional approach would be to encode these as abstract vectors injected directly into the model. I chose this method instead because it's both human and machine interpretable, which makes it much easier to tell what's happening when debugging recorded games. Together, these encode enough information that the model can make decisions without any other form of memory. Now let's talk a bit about the reward function. Exploration and total levels were discussed earlier in the video. These were by far the most important rewards, but there was actually 7 used in total, and even more that were tested but not ultimately used. There isn't enough time to cover them all in depth, but the general criteria for all of them is that they broadly encourage playing the game well rather than focusing on a specific moment, and they shouldn't be easy to cheat. All this information about the game's state is obtained by reading values from the Game Boy emulator's memory. The game doesn't have any kind of proper API, but most of its memory is statically allocated, so variables can always be found at the same memory address. The PRET project has done an amazing job of reverse engineering the game's source code and mapping out its memory. As a tangent, it's honestly mind-blowing that all of the logic, graphics, and audio for this whole game is stored in less than 1 megabyte. This is smaller than a single photo that you take on your phone. Anyway, understanding the AI's behavior is essential for realizing its full potential. One of the best ways to do this is through visualization. So how were the visualizations used in this project made? First, key information like player coordinates and Pokemon stats are recorded at every step in every game. Next, all of the games need to be rendered onto a single map. The game itself doesn't contain the concept of a single map with a global coordinate system. Rather, the world is divided into chunks of 256 by 256 tiles. The game tracks the player's local coordinates within a chunk and which chunk the player is currently in. So after deriving a mapping from local chunk coordinates to global coordinates, all games can be rendered together. The actual rendering itself is a rather slow NumPy program which places sprites at the coordinates the players are moving, choosing the appropriate sprite based on the direction they're moving, and interpolating between each tile. To render the giant game grid, a Python script is used to generate an ffmpeg command to tile together thousands of videos using a rather well-endowed server. The flow visualization was made using the same player data by aggregating all movements on every tile. Combining all these strategies, it's possible to train a reinforcement learning agent to play a complex game using only modest resources. But what else could be done to further improve this process? Let's take a moment to consider how this could get easier, cheaper, and faster in the future. First, as mentioned earlier, the AI in this project started learning from scratch with no prior experience at all. In the future, it will likely be possible to apply something called transfer learning. This is when a model is pre-trained on a large, broad dataset which can then be leveraged for new tasks very efficiently. In the past, this has revolutionized the fields of computer vision and natural language processing. There's been some interesting early work applying this to RL, but it hasn't really landed yet. This is partly due to a lack of large, diverse datasets for these types of tasks. However, it seems like it should be feasible to extract a useful world model from a big enough dataset. Here's a quick experiment I did using clip for zero-shot classification of game states. It's easy to imagine how this could be used to create reward functions for new environments without special access to their internal state. It's probably just a matter of time before large multimodal models start to have a huge impact in this area. A second method of interest is directly learning environment models. A couple notable works in this area are MuZero and Dreamer. These approaches offer a huge improvement in data efficiency by learning a model of the environment itself and optimizing the policy against the learned model. I recently ran some experiments with Dreamer v3 and was very impressed with the results. A third method worth mentioning is hierarchical RL, which decouples low-level control from high-level planning. This allows fine-grained movements and long-term strategy to be handled by separate mechanisms. So those are some ways this technology could be improved in the future. To wrap up, let's walk through how to run this AI on your own computer. Alright, so this is the repository linked in the video description. First step is going to be to download it. You can do this using Git, or by downloading the zip. The next step is going to be to legally obtain your Pokemon Red ROM. You can find this using Google. It should be a 1 megabyte file ending in .gb. I already have mine here, so we're just going to move into the root directory of the repository, and we're going to copy it in here. And I'm going to rename it to Pokemon Red.gb. Now the next step, this one is optional. We can create a Conda environment. So we can just name it whatever you want. Accept that. And then activate it. And now the next step is the same whether you created the Conda environment or not. We're just going to install the requirements from the requirements file like this. All right, when that's done, we'll just make sure we're in the baselines directory here. And then we can run the pre-trained model script, which is going to be run pre-trained interactive. Will take a few moments to start up. Now the game should open up and the AI will start playing right away. In this mode, it won't do any additional learning and will only play based on the experience that it already has. You can actually interact with the game at the same time that the AI is playing it. So for example, I can interfere with it by using the arrow keys and forcing it to go into this corner. This mode is very fun because you can put it into different scenarios to see how it handles them. If you want to disable it entirely, you can edit this text file. So by editing this text file, agent enabled .txt, if we change this to no and save it, the AI will stop having any actions, and now we can take full control of the emulator. And if we edit this file back to yes, it will reactivate and continue playing. Now if you want to train the model from scratch, you're going to want a lot of CPU cores and memory, but assuming that you have that, the script that you'll want to run is run baseline parallel. This will start running multiple emulators headless without any UI. And this will take quite a long time. You might need to wait many hours or even days to see positive results. If you want to change any of the basic settings of the emulator or the games, this configuration, which can be found in any of the run files, allows you to do this. Other files in the repository allow you to make any changes to the reward function or to modify the visualizations. If you have any questions regarding the code, feel free to open an issue on GitHub. And with that, we've reached the end. Thanks for watching. I hope that you gained some insight into reinforcement learning, or maybe even your own psychology. I really believe that these ideas are as useful for understanding our own behavior as they are for advancing machine learning. If you'd like to support this work, see the link in the description. Bye for now.